starting. It's not an animation, it's my clicker. Those are the slides. All right, I have a question. Who the hell is that person? Who is a protocol engineer? It has to be something really, really awesome and fun, because there's like tremendous amount of job offerings somewhere on the web, and the salaries on them, they just skyrocket. So, who is that person? And what do they do? So, protocol engineer usually operates in this vast and enormous and scary place called distributed system. By the way, this image was created yesterday by ChatGPT, and I'm pretty sure it was trying to summon demons. I'm not responsible for arrangement of this topology. But yeah, protocol engineer, basically that's what they do, that's where they operate. They try to provide something functional to the users in the distributed systems, which is really, really, really hard, as some of you probably know. So what they do is they try to design, implement, and evolve a system in this vast, magical space. Their work is to somehow orchestrate a protocol, something that will be valid, something that will withstand arbitrary failures or people trying to be nasty. And at the same time, even when they do design a protocol like that, something which will be robust and will withstand all the model checkers and all the formal methods and whatnot, there will still have to be someone who will implement this. And going from that overall bird view of the system into an actual implementation is really, really, really hard task. So I'm thinking it's kind of hard to define what a protocol engineer does precisely, and this will probably vary from company to company. But I bet that if you are in a room with a protocol engineer, there will be signs, and you will know. Because that work is extremely, extremely complicated. My name is Paweł Szulc, but on Twitter or X or GitHub I'm called Paweł, and I will try to talk about a little bit of difficulties in writing distributed systems as a protocol engineer and how this new emerging paradigm called choreographic programming can help. The paradigm is fairly new. It's been around for at least 2 decades. But because this is Lambda days, we'll try to make a more functional approach to it. If there is one, are we production ready? And is it really, really helpful? And I guess we will see. So are you guys ready? Yeah, that is so awesome because I'm not. I've been working on this presentation literally day and night. And this is not me making a grammatical mistake, which I know there will be plenty. When I say day and night, I mean singular, not plural. Yesterday and during this night. And I finished 10 minutes ago. So, if there are errors, rough edges, sorry. I tried, I really did. All right, so protocol engineering, as I said, it's really, really hard. There's basically this tremendous amount of stuff that you have to think about. You might have a researcher who will write you a paper, and you just have to implement this. You might be thinking, well, half of the work is done. Well, not really. If anyone here implemented at least one research paper, you know researchers tend to forget about this thing called physics. Sometimes things travel faster than the speed of light and whatnot. You have to deal with that. Or maybe you design your own protocol. Maybe you sort of have a problem at hand and you've designed the protocol and you think it will work. But will it? How would you know? Well, maybe you draw it on the whiteboard. But does it hold? Is it safe? Does it hold all the invariants? Is it live? Maybe you will throw at it some model checker like TLA plus or Quint. Okay, you might have some guarantees that it works. But then you have to go from that design to the actual implementation. And it's not a trivial work, because while you're designing your project, you have this bird view of the whole system. You see how messages are flying around between nodes, and everybody is happy, and you sort of see how the whole system progresses, which is great. But then, when you implement this, when you actually write an actual running code, you have to project that into individual nodes, which is hard. And on top of this, you have to do it in iterations. Because you might design a protocol, you might provide an initial implementation, maybe you will do some simulation in front of it before you write some implementation, just to see if everything is working correctly, and then it breaks, and then you have to repeat. And that iterations, this is a repeatable cycle, so it's really, really hard. There was this paper published about problems of protocol engineering, and the problem of, and some quotes, how hard it is. Some of them, if you look at them, you think they might be things they really are. And I only did this so that your brain still is here with me. And I was bored at 3 a.m., so I was thinking, well, what the hell? Anyway, the pain is real, even if the quotes are not. The pain of writing software like that is not always not fun. Well, it's challenging, and that's why it's fun, but it's sometimes painful. So, in order to demonstrate that problem of going from this bird view of a protocol into an actual implementation, I have an example, a simple one. Imagine a simple handshake protocol. You have two nodes. They would like to do a handshake, like say, like, hi, would you like to connect? The other one would be like, yes, this is awesome, let's do it. And yeah, that's pretty much it. The initializer sends a hello message, and then the responder sends back another hello message. And that's it. Hopefully, straightforward, nothing really too complex, but if this amount of text is already complicated, I have a diagram, because why not? So, is this sort of protocol simple enough for us for this presentation? Hopefully. You guys with me? Awesome. Okay, so if it is simple, let's now try to implement it. It's nothing really like, I know this is nothing you would normally run in production, but it is mimicking some of the issues that you might see. So imagine that we have an API, and obviously this API is some form of abstraction of when you want to send a message to a node of a given ID. You might receive a message from a given node, or you might receive some message from a node you haven't really talked to yet. So this is not a, this is just for example, so this is like treated as a pseudocode. Obviously it doesn't deal with errors properly or timeouts or whatever, but give us an entry point of how we could think about implementing those two nodes, the initializer and the responder, for that simple protocol that I just showed you. So if you think about it, it's not really that complicated, right? So our initializer will create a message, hello. It will send that message to a node with a given ID, and then wait for response. And we don't really care here about the response, so we can just ignore it. But that's pretty much it. That's the whole program that you have to write. And the other node has to do the other part of the protocol. So they wait for a message of type hello. Once they receive it, they create their own response, and they send that response to the other node. And that is it. And I am aware that this is the simplest protocol that I could think of during that presentation. And it's not a lot of code, and if there is an error in this protocol or the implementation, it probably will be trivial to spot. What kind of errors we can expect in this kind of system? Let's say the protocol itself is correct, right? Because it's a simple one, back and forth, a ping-pong sort of a protocol. But implementation might not send a message or expects a message of a different kind. There might be errors like that. In a simple scenario like this, obviously probably will be easy to spot during the pull request review. But if we complicate this example a little bit harder, and we are not really pushing the limits, but we are closely getting to something that is maybe a little bit more closer to the real world. So imagine a slightly more complicated protocol where you have two nodes which are going to do a handshake, but after that handshake, if they connect to each other, they will start communicating over other protocols that you have in your system. Not one, but more. They're like more sub-protocols that the system will run. Now, the problem is that node A here might be talking about in the language of protocol A and B, whereas node B here might be talking in protocols B and C. So during the handshake, we need to exchange protocols. So not only we're interested in the fact that we're going to have a conversation later, but also which protocols are we going to use, and in which versions, because those may vary, right? So the idea is simple. You send hello. The other node makes a decision whether they want to connect. Let's say they have a limited amount of resources. TCP is, I guess, expensive. But if you're happy to connect, that's fine. Then you send your list of capabilities, which is basically a list of a protocol and a version. The other node looks at this, compares that to what they have, finds a common set of protocols that you can have a conversation, and in which version. And they send that back. So this is slightly something closer to what you might actually find in the real world. And obviously, there are some edge cases. So if the limit of connections is reached, you reject. Or if you couldn't really find any protocols that you can have a conversation with the other node, you also reject. So all that simplified on one slide already looks complicated, but the implementation is even more complicated. And I'm not going to go through this because it's kind of boring. But the idea is simple. You send hello, you receive a message. If it was reject, the initializer. If it was rejected, then, well, it's rejected. Then we're done. If they actually agree to handshake, they give us a list of capabilities. We have to compare it with ours. If we cannot find any, we reject. Otherwise, we send acknowledgement, and we're happy. The other node does the other part of the protocol, which is they receive a message, they see if they can actually connect. If they can, they send a reject. If they can, they send a list of capabilities, and if they receive acknowledgement, now they know on which kind of protocols they can have a conversation. This is already, I would say, a potential place for errors. Because in that iterative process, when you create protocol, you provide implementations, you modify it, someone gives you a use case or maybe sub-case of the protocol, it's easy to create an error, and it's really hard to spot it until you run it. And it's kind of problematic, because there are no tools that will just well, there are, but, well, it's a different, I guess, topic. But it's hard to go from that idea on a whiteboard to implementation, especially if it changes constantly. And making an error in a system like that is trivial. Especially, we had here only two nodes, or maybe two roles. In more complicated systems, there are more roles than that. So even though the protocol was simple, the implementation may actually have errors. To the rescue are choreographies. So I guess the main part of this talk. So I have a teenage daughter. So when the first time I heard about choreographies, the very first thing I thought of was this. And but to be honest, that metaphor is not wrong. The idea is that the same way as a dance choreographer looks at their dancers and try to orchestrate a choreography with limited resources on a limited dance floor with some constraints, but they have a bird view overall dance that the dancers will perform, and they need to have a way to directly give the individuals information how they should do it. And the same way, the choreographic programming does for programming in distributed systems. So the idea is simple. You have some form of language that allows you to talk about the bird view of your protocol that you try to implement, and then automatically out of it, you get running individual programs. So, you write a single choreography that globally describes the behavior of your system, and that in that choreography, everything is sort of described, including the data, locality, local computations, everything. The syntax from the sort of early papers when this paradigm was described resembles a little bit of, well, at least for me, PyCalculus. There are others who will point to different papers, but the syntax, I would say, is simple for the choreography. You have Alice, you have Bob. Alice sends a message to a Bob. What message? M. Trivial as that. And initially, there were solutions using this paradigm that allowed you to exactly do that. So in our simple handshake example, we're back to the simple one. You would write a choreography which would look like this. You'd have an initiator which sends a message hello to the responder, and the responder responds back with a hello. That would be your choreography. That looks very similar to the sequence diagram that we had before. So a valid question would be, from the audience, what's the point? Because kinda the sequence diagram, at least for me, speaks more than that little syntax over here. The main point is something which they in the paradigm called an endpoint projection. An endpoint projection, or in short, EPP. And that's this is the sort of the key novelty of the paradigm. That you, as a designer, have an ability to look at the choreography from the bird view, and the system that you will use, whatever that will be, knows how to translate that automatically to the individual notes with magic. Does it make sense? Sounds ridiculous? Is it possible? Like, what are your thoughts? Well, let's see. All right, so this is a blueprint of choreography. Send a hello and wait for a hello back. With EPP, you project that for each and individual role in the system. So in the choreography, we had initiator and a responder, and we were able to communicate in that syntax what they do and how they operate. But then when we project that, we projected, give me a program for the initiator. And that builds a program for initiator that will just work. The same will go for the respondent as well. So you have a closed loop in which you can reason about the system, and that automatically creates the implementation per individual node. That solves a lot of issues. And as hopefully we will see later, more than the problems that we described. So, you might be asking, okay, so can we see some code already, right? And I get that. So, initially the choreographies, they originated, for the reasons I don't understand, in object-oriented systems. And there are some implementations provided for Java, and now they're sort of like boomed in recent years. You have for Rust, you have for Clojure, you have for OCaml. But they initially started in that Java sort of ecosystem. And they were working in a way that they've provided their own language. So the choreographies would be described in their own language, and then they would be compiled or interpreted to individual nodes, which would run, for example, as a Java code. We will talk about something else. A research paper and a library in Hackett called Haskell, which is implemented in Haskell and you can use it today. So that paper has functional choreographic programming for all, which actually became a functional Perl and was presented on the ICFP in 2023, won some awards. I mean, distinguished paper. There's a wall of text here. You don't have to read it, obviously, but there are some keywords which are kind of fun in that abstract. So already at that time, so one of the novelties that you have from this implementation, and we're going to look at it, don't worry, I have code, which compiles, by the way, because I checked. This is the first approach to this idea in which you don't have to have separate language. It works as a EDSL in your Haskell program, so you can reuse that in your existing project. So that's one thing, but also the other novelties are, at that time, within the community of choreographic programming, within that community, they were starting to discuss, well, more complicated cases, I would say. So they would talk about higher order choreographies. Can I have reusability in my choreographies? Can my choreography return a choreography that later on will be interpreted? The very first choreographic programming languages, for example, also didn't have any notion of polymorphism or like data locality, in a sense that you would create choreography, but you would have to almost immediately name your notes. I'm going to have this, this, and that's it. With this tool, we get polymorphism for free. Now, you will see that in a minute, and the way I'll try to approach this library is in a way that I will try to show you the syntax of it, which I don't think it's enough for you to already have fun with the system, but then we will also look at how this is implemented, and you will see how the implementations for most of that magic are trivial, because they stand on the shoulders of giants, and they've built on top of things that we, as Haskell programmers, already have. Well, some of us love, some of us don't, but I'm not going to spoil that just that yet. All right, let's have a look. Let's have a look at that simple handshake example and how we can implement that in terms of choreography and how we can project this into a running system. So this is the function that's going to describe the choreography. Let me just check time. Okay, 20 minutes, fine. This is a function, and you will see it takes two arguments. Those are proxies from initiator and responder. And initiator and responder are types, but not any kind of types. Those are symbols, so type level strings. Now, if this is already extremely complicated, we can simplify it for now. So what we can do is, and by the way, it returns this choreo type, which is closed over some monad, in which local computations will be executed. We can simplify it for now. So I can replace the monad with just an I/O, when things are simpler. And maybe we can just remove those proxies as well. And this is still valid. This is still we can still implement something like that, but we will not take full advantage of what we have from the system, from this library. What I mean by that is that if we have choreography that we know here returns a unit, runs over some I/O, but we don't provide the actors, the roles in the system, those will have to be embedded. So let's say you have two nodes. You have node A and node B, and you name them. You provide a unique identifier for those nodes by name, and you use type level strings, as you can see here. That means that in this choreography, if there's any node in this choreography, we will have to use them explicitly. So whatever the API of the library is, I haven't showed you that yet, we will just reference node A and node B to do something over I/O. But this is not taking advantage of the system. I would rather prefer for the signature to be full in this presentation. Because the key difference is that I've provided you choreography and I said that just in the signature of the function, you can read the actors who will play a role in the system. There is an initiator, there is a responder. They will have some computation here right now over someone at M. Apparently, we don't even care at this point what that is, that M. So once we have that, we can then call this function that we've created, the handshake protocol function that takes 2 arguments, polymorphic. We call it, and now that gives us a handshake that is tailored for those 2 nodes, A and B. But we can tailor it for other nodes in our system as well. Once we have that, we call our function EPP on it. This is the projection that I talked about like a moment ago when we were talking about choreographies. And that is almost it. What is a network program? Network program, so after we do a projection, it gives us a network. We will see in a moment what that is under the hood for people who are interested, hopefully everyone here. But think of it as an abstraction for now that knows how to send things over the wire, receive things over the wire, broadcast things over the wire, and run some local computation inside a specific node. So that abstraction network allows you to do that. With that, you can go from the bird view of a choreography to a projected program of an individual node. And that is it. That is the whole API. So now let's try to implement this. The implementation, as you remember, we're supposed to send hello and then get hello back. And with the functions that we get from the library, that is essentially what we do. We say that on the initiator, locally, we will call the function makeHello, which generates a hello message of type hello. And that representation of that locally created message initiator is held within this variable hello request. Now, hello request is of our type message with extra meta information. That meta information is saying, I originated, I live on the initiator. This is where I am. Then we have this squiggly arrow, which represents sending things over the wire. So I'm saying I'm sending from the initiator my hello request to responder. The responder locally computes their own hello message, and they respond back to the initiator, which finishes the protocol. Now, a really cool thing about this is that this is no longer an image that I've created using a sequence diagram. This is actual code with actual type level information in it. So if, for example, in my choreography, I make an error. So after the initiator created their own hello message, which is called in hello request, I make an error and I say, it's not that the initiator sends this message to the responder, it's the other way around. It's the responder sending this message to initiator, which is obviously wrong because it's not the responder who created it. It lives on the initiator. The only initiator can send it. We get an error message. It's Haskell, so it's not going to be great, but it's actually telling us something. It's, if you look closely, really closely, you can get to where the problem potentially is, which I think is really great. If you look at this protocol, you might be thinking, oh, okay, but if initiator sends a hello message to the responder, does the responder in this protocol potentially, do they have to create their own hello message? There's no extra meta information. There's no information. Could they just like grab the message and send it back? After all, they own it, right? The responder got the message. It's like, hello, shit. get it back, right? Can we just reuse it? Well, let's have a look. So instead of like ignoring the message that we get from the responder side, we're gonna store it. So we got that hello back. So this got hello is this hello message that the initiator set, but got hello variable now holds meta information I live on the responder side. So now when the responder sends the same message back to the initiator, which is valid, this function compiles. This is still valid because we track that information of data locality, how they travel throughout the network. We have the whole system. This is the beauty of it, that we know everything at this point where we orchestrate the system. And as I said, okay, we can actually now run it. So the difference for us to run it, I will change monad to monad IO. And the reason for it is I want to, when we create a message, I just want to print something to the console, or we see that something is going on in the system. So this is the whole thing, right? This is the same choreography that we saw a moment ago, but it just prints stuff to the console whenever messages are created or received on the other end. So far, so good. You with me? Like 10 minutes, and we're done. A break and coffee. All right. So we have everything. We can project this to this concept network. We have no idea what that is just yet. And now we can create our little tiny program that will run this protocol. So the idea is simple. I've grabbed an argument because I need to know which node I'm running right now. Either this is node A or node B. So if I know on which node I'm running on, I can take my handshake protocol, which is tailored for nodes A and node B. I can do the projection using the EPP function for the node that comes as an argument to the main call. And there are numerous ways of how we can interpret the network. So there's no one way to run the network abstraction. There are various implementations. You can run it on threads if you want to run a simulation. You can run it on sockets if you want to be closer to the metal. You can run it sort of in a testing environment where you spawn a servant server that acts as a network layer. So there are various ways how you can run it. This is one of the ways. So we created 2 servers running on 2, expect to run on 2 different ports, and we just run our program, the network program we run on the system. That is it. We've created choreography, we've projected, and we run projections. That is all. And I have a live demo for it. Well, luckily for us, this demo never fails because it's on slides. So I'm going to spin node B. Node B is running. It awaits messages. I'm going to spin node A. Node A executes, it started running, and it initialized, it sends the message hello over the network to node B. And node B receives that message, it's responding, and the program is done. And we're finished. Which I find great, which I find awesome. Now, this is the API. Now we have, how much time do we have? 10 minutes, it seems, or 9, to look under the hood. So for those interested, how it works. So, under the hood. So under the hood, Choreo is a free or freer monad. And that runs over language Choreo signature, which has basically 2 abstractions. Local, for local computation, and for communication from sending thing over to wire from one place to another. If you haven't seen free monads ever, or you want to like to refresh your knowledge, a 101, but very quick one. So whenever you have a type thing, a value of a type free or FA, what that means is you have a program. Great. That program works on a language. What kind of language? It's defined by F. So the only things you can do in that program, so you have a value of freer FA, the only thing that this program is capable of doing is whatever is defined in the F, and the value that's going to produce is an A. That's it. So we have ways of taking our language and lifting it into our program, and we have this nice little function, interpret free, which means that if you have a language with some vocabulary in that language, and you know how to go from that language to some effectful monad, like an I/O, for example, we will know how to go from your program defined in that language to that same monad. And you get that for free. That's the joke. You get it for free. Magically, magic happens and it just works. So, 101 is done. You were given 3-year monad lecture in more than 1 minute. Now we can look at the implementation that we have under the hood here. So the language for choreography has only 2 verbs, local computation and communication. So either you send things over the wire, or you compute something locally on a given node. You will also note that there is this ampersand. We have, for example, A at L. If you look at comms, you will see that in comms, we have 2 actors, L and L prime. We send stuff from L to L prime, and the value that we're sending is not of type A. It cannot be string or user or hello message. It is type message annotated, that's on L. And that annotation, that ampersand, is part of the library. It's not additional Haskell extension that I haven't heard about. It's just part of this library, okay? So, but we're looking at just at the type signature, you know that the value A lived on L, and once we send it to L prime, now it will live on L prime. And that's how the choreographies track that data locality where those individual values live. But having said that, now we have 2 functions. Locally is, you remember 2-3-year? I said, like, if you have a language, you can lift it into a program. That's what locally does. It takes the local construct and lifts it into free. And the same for squiggly R. Squiggly R is just com, and locally is just local. That's what it is. We are reusing, so if it's too hard, I don't blame you. Like, a separate talk about free monads is its own thing. But if there's only one thing you will take from this section of this presentation, is that this is well recognized in the community, researched, and there are libraries that do it very well. So we are standing, as I said, on the shoulders of giants to provide functionalities that other choreographic languages had to rediscover. Now, EPP projection is really just that interpret free. That's it. If you remember, the interpret free was saying, if you know how to go from your language to some monad, I will know how to go from your program to that monad. And if that monad is network, so another abstraction, you don't have to go directly to I/O. You don't have to take choreography and go directly to I/O. You can take choreography and only project part of the functionality that is responsible for a single node. And that's what we do. That's really what it is. The EPP is a single line of code, interpret free, with a handler that knows how to do it, and we will not go into details if you want. There's obviously this project is open sourced. And apparently this happened. So network on its own is also a free monad with its own vocabulary. So it knows how to run locally stuff on that particular node. It knows how to send things over the network. It knows how to receive stuff from the network, and that is it. Given 4 minutes. Network, yada, yada, yada. This, we will just drop that. How is that implemented? I want to get to this. In the 4 minutes, I'll manage to do this. The question is, this looks awesome, hopefully. Is it production ready? Is it? Well, as you know, I started this presentation working on it yesterday. I thought that a good idea will be reuse a software I've written using this 4 months ago. I've spun my project, which compiled 4 months ago, and I got this. And so that was not a good start to present, a production-ready software. The fix was simple, and it's already merged. It was just, there's one person in this room probably who recently, I know who that person is, recently published new version of Servant, and that broke this project. But anyway, fixing this was easy, but that gives a hint that, oh, okay, there's something wrong, right? Like this is, it's a little bit of smell, if you can say it like that. This project got enormous traction from community when it was published. People were really excited, and it even appeared on an Unfolder channel. If you don't follow Etzko and Andres, you should. This is like the channel for you Haskellers, newcomers, and seasoned Haskell developers. They really liked it. It's a really good presentation, I think. And there were some issues raised about serialization, because it sucks. It doesn't have serialization. It uses read and show. That's not production ready. There is this ergonomics on unwrap, which I haven't talked about. Kind of like deliberately didn't show you the issue with that. It's not production problem. It's just like syntax kind of sucks in that place. There is another there's another concept which I also didn't show you, which is called condition. And it abstracts away over some decisions that the system does. So if I were to give you a summary of it, think of it as languages that used to have a go-to in them, and now you have recursion. So an abstraction above something that is still needed in the running system, in a Turing-complete system. The same way conditions are a little bit of abstractions where you can get rid of some of the messages in your protocol because they are provided by the choreography themselves. But we haven't talked about it, and they are great, but the implementation uses broadcast, which is not always great because it just like sends too many messages altogether. So there were issues that community was raising. One of them, I mean, this is great that they use their own home-baked free monad, but there are, Alexis King will tell you why that sucks. And there are better ways to do it. And I don't really find a production-ready interpretation of network to I/O, something that would reliably call on my system. And some other stuff. Like there's one of the beauty things we can get from choreographies is the fact that we can really, like those sequence diagrams, they can really be created automatically. I've worked for a few months on a project that used choreographic programming in production. And ML, machine learning, I know this is cool, but they were doing this before this was cool. And they've written this in Python, and it worked, but no one could maintain it. And they used choreographies to re-implement this in Haskell, and it worked wonders, because now they could reiterate over their system that is really, really complicated. And they get so many things for free, like sequence diagrams. When you have a complicated systems with a lot of machines that do a lot of heavy lifting and machine learning and whatnot, having an ability to just produce a bird view of how the system looks today is awesome. And we cannot do that in here just yet, and there are some reasons. So I've asked a question, what's up? And they were very nice, giving a honest and I think very good answer. And the answer is following. This is a research project. They tried to show that having a production-ready system that will do choreographic programming is trivial, which they did. And they are right now working to enhance it. They are working on new ideas, on making this more robust in terms of the abstraction that you as developer will get. And they are really pushing that research forward. But they are sort of researchers. They don't have a production-ready system that will be backing this up. So now that we know that is a research project and not a production-ready project, the question is, what can we do about it? And there are some Lambda talks, Lambda-based talks I did over the years. Some about process calculus, the formalization, about making a sustainable system that works with complexity, with polysemy. Alexis King told me, well, this will suck, but luckily, Andrzej Rybczak, and shout out to a guy from Poland for making an amazing library, came out with Effectful, and now we have Haskell. So we have a way to reason about a system on a single node. Now we have researchers working to sort of have this being spread over the distributed system. Now there's this only one thing we're missing. But I think we have all the building blocks. And you kind of get the logo, you know what I'm getting at. If we had something like this, that would be amazing. And I think it is simple to have version 1.0 or 1 running. Now, if I did my job today, which I'm not certain, but if I did, I hope we will have it soon, because there's already someone working on it, and I hope it's one of you. Anyway, that's all, folks. My name is Paweł Szulc, Ncompound on Twitter. Thank you very much.